Okay, welcome to part two of our lecture video series for Wednesday, May 10th, where we're now discussing phase diagrams. So we're no longer looking at phase change diagrams, we're looking at phase diagrams. So let's define what a phase diagram is. So a phase diagram, this is a curve that shows the effects of typically pressure and temperature on the phase of a substance. So if I exist at some temperature and some pressure, what kind of phase am I likely to be in? This is what this phase diagram is going to show. So each substance has its own unique phase diagram for reasons we're going to talk about coming up next. And when reading a phase diagram, the curve that you're going to be looking at, like the actual line of the curve, represents a series of pressure and temperature conditions at which a phase equilibrium is established or exists. Where a phase equilibrium is just like we talked about with vapor pressure. This means that we have two or more, we'll get there, phases existing at the same time. So let's look at a general phase diagram. So I'm just going to draw like a non-fancy phase diagram. So they will kind of all have this general structure, like they will all kind of look like the following. There will, of course, be minor differences in like the nature of the curvature of each of the curves I'm about to draw. But you will see something like this. So we have pressure and temperature. Okay, we tend to see something like this, followed by this, followed by this. Guess I should probably extend my axis or make this a little bit smaller. So let's do that. All right. So not perfect. This is kind of a general sketch. So let's talk about what's going on here. So I'm going to start by looking at kind of these regions between the curves before I think about what's going on in the curves, like on the curves themselves. And again, I am not happy with this shape. Maybe it's because it's Taurus season, but I'm stuck on this looking like the Taurus constellation. Okay, there we go. I'm a little happier with that. So let's start with this region here. So why don't we look at all of the pressure and temperature data points that are found in this region of the curve. So this is a series of temperatures and pressures, right? I could put any point here, right? This would be associated with some kind of temperature, and some kind of pressure, right? So you can imagine I've got a bunch of different temperature and pressure points graphically posted here. And let's ask ourselves what kind of phase is most likely to exist at kind of, I don't know, mid to high pressures. And looking at our temperatures, let's see here, I don't know, low to mid temperatures. So here we have, again, maybe I'll write it over here on the right. We've got mid to high pressures, and we've got low to mid temperatures. So let's ask ourselves what kind of phase is likely to exist at low to mid temperatures and higher pressures. So high pressures, meaning you are pushing something together, right? You've got all those molecules that are nice and tightly packed. Low temperatures, those molecules are not in motion as much, right? So we would probably expect for our phase at these conditions to be a solid. So in this region of the graph, this is where you see just the solid phase. So at any of these temperature and pressures, you will find a substance in the solid phase. Okay, let's do something similar for this region of the curve. So again, these are all different temperature and pressure points. I could identify a point in this curve that would be associated with some temperature and some pressure, right? And if we kind of look at the range that we're looking at of pressure and temperature, this looks like our pressures are still kind of similar to that of our solids. So we've got mid to high pressures. But now let's look at our temperatures. So our region kind of encompasses from here to here temperature-wise. So this is now mid to high temperatures. So kind of middle of the road, right? We're not looking at really low temperatures or really low pressures, nor are we looking at super high temperatures. We're kind of looking at enough pressure to keep our molecules together, but enough temperature to keep those molecules in motion. So that is going to be our liquid phase. So at any of these temperature or pressure points, we're going to have liquid. Leaving behind for us in the remaining section of this curve, all of these temperature and pressure points that range from low to high temperatures, but in particular, low to kind of mid-ish pressures. So we have enough temperature, enough thermal energy to keep our substances in motion, but we do not have so much pressure being exerted on our substance that those molecules are forced to stick together. This is going to be our gaseous phase. And so in each of these regions on the graph is where we see the three distinct phases. Now remember, if we are looking at a phase diagram, we are looking at these curves. So these curves, meaning these lines drawn here and here, are what we care about. So if we are looking at this curve here, and I'm just going to kind of make my pen a little more fat there we go, this curve here. So this is a series of temperatures and pressures at which two phases exist at once. Specifically, we are in a phase boundary between the regions that are bounded by that curve. So phase equilibrium between solid and gas, meaning at any of these temperature and pressures, we see both solid and gas existing in equilibrium with one another. Okay. What if we were to look at this segment of the curve? So up here. So again, these are other temperature and pressure data points. So this curve is made up of a series of points, right? And since we are looking at a curve that is a boundary between the solid and liquid phase, that means that we have a phase equilibrium set up between these two phases, meaning at these temperature and pressures, we see both solid and liquid present. All right, so we've got down here temperature and pressure data points where solid and gas exist. And then up here, we've got temperature and pressure points at which solid and liquid exist. This leaves behind this curve. And this curve is a series of, again, temperatures and pressures, except this curve is now the boundary between liquid and gas, right? So we've got a phase equilibrium that is set up between the liquid phase and the gaseous phase, meaning I see both at these temperature and pressures. So I will see not only a liquid, but I will also see at these temperature and pressures gas. So it's cool, like you'll see literally both phases existing at once in this equilibrium. And that's what's going on each of these curves. This is what really kind of matters to us. So here we've got that curve. Here we have this curve, this phase boundary. And then here we have this phase boundary here. Now, there are a couple of really interesting points on this particular diagram. And I think the one that you might be able to clock kind of right off the bat, so let me just label this real quick. Solid, liquid, gas. But the really interesting point is where all three of these curves meet. So this point, very creatively, is called the triple point. And the triple point is a single temperature and pressure data point, right? I could figure out what that is by looking at my plot. Like I could find some associated temperature and pressure. And at this single temperature and pressure, all three phases exist, capital backwards E exists at the same time, which I think is just really rad. So I will try to find a video of this going on. Like I want to show you what this actually looks like. So at the triple point, all three phases exist at the same time. Okay, there is one more point on this curve that is kind of relevant. I mean, you're not maybe going to use it in Chem 210 or even Chem 220, but it's this point up here, kind of where that liquid gas boundary line goes away, or like finds its upper limit. So this point that I've indicated with a little star, this is what's called the critical point of a fluid. And this is a temperature and pressure point after which, like if we surpass that temperature or that pressure, our liquid behaves as what's called a supercritical fluid. Okay, my marker is really fat and it's bothering me. I'm going to turn it back down. Okay. So supercritical fluids, they're kind of interesting. So let's devote a little bit of time to them. So supercritical fluid, these have interesting properties in that this is a phase where distinct liquid and gases do not exist. And they have, sorry for the long pause, they have properties of both gases and liquids. So it's like they're not exactly a gas and they're not exactly a liquid. It's like phase or substance or phase of matter that behaves kind of like both a liquid and gas. So for example, what might that look like? So some properties of a supercritical fluid, just if you're curious, they have low viscosity, meaning they have a pretty easy time flowing. So they flow freely, but yet they also have like a really high diffusion rate. And it's kind of like a supercritical fluid can be also, let's see here, super compressible. So low viscosity, high diffusion, and high compressibility. Compressibility. So it's more important that you're able to recognize the critical point of a phase diagram than it is to know exactly what a supercritical fluid is. Just know that at the critical point, like any temperature and pressure found beyond here, like we can keep going with temperature and keep going with our pressure axis, we will no longer be either a liquid or a gas. We will be a supercritical fluid, which is some kind of fluid that's kind of like a gas and kind of like a liquid in that it has behaviors of both. But again, more important that you could identify where that is on a phase diagram. So here's a general phase diagram. Again, every substance is going to be different, right? They'll have different shapes. Maybe some of these curves will be a little steeper. Maybe they'll have little hooks. And all these are things that are experimentally observed and determined. So like we had to change pressure and temperature to look at what our phases were. And water is an interesting case we'll look at, I think. Let's look at that on Friday. I'll show you the phase diagram for water. But yeah, this is a phase diagram, so you are expected to know how to piece out these different regions, identify what type of phase changes or transitions are happening along each of these boundary lines, and identify both the critical and triple point. Okay, that's phase diagrams. So now we have talked about the gaseous phase. We've talked about how substances can undergo phase changes. Let's talk now about some really important things that are going to help us in our conversation about the next phase, which is the liquid phase, and those are intermolecular forces.